Good morning all of you. My name is Dr. Deepak Yadav, and today we are going to study one of the topic of digital system design, that is combinational circuit. And these combinational circuit are a very basic circuit which are used in digital system design, and we are going to focus especially on the adders over this lectures. So this is the basic combinational circuit that we are used in our digital system design. There is some inputs and the corresponding output we are taking, maybe n inputs and n output is taken, and there is no feedback in the combinational circuit over here. Combinational circuit is made up of different logic gates which perform different logic function to perform some specific task. Like for the adder circuit, we have different logic gates that perform the addition of 2 or 3 input numbers and produce the output as a sum or carry at the output. So this is the basic block diagram of the combinational circuit over which in which there is multiple logic gates to perform different logic functions. Next is the first topic is the analysis of the combinational circuits. So in the analysis of the combinational circuit, there is two type of circuit analysis. Circuit analysis and circuit design. So if we have already given circuit over which we have to perform the analysis, how this circuit perform, is come into the category of analysis of the combinational circuit. While if we have a problem statement and we have to make the design of the circuit, then it comes in the category of design of the combinational circuit. So first over here, let us take an example of this combinational circuit which is given and we have to analyze this circuit. So how we can perform? We have to produce two things: the function at the output, that is over here and the over here, and the corresponding truth table of all the combination of the input that is possible over this circuit. So here if we see, there is only 1, 2 and 3, that is A, B and C are the A, B and C are the inputs, and two possible output F1 and F2. So in the truth table we have A, B and C input and F1 and F2 as the output. So for every combination of A, B and C, that is, it is 3-bit number. So we have 8 possible combination up to 111. We have to find out the value of function F1 and F2 with the help of this circuit. So for doing this final truth table, we have to generate the function at the output. What is the function at the outputs, and then in that function we have to put each time the value of the input A, B and C, and the corresponding output are written over here. Like if we take an example of for producing a function F1. So for the function F1, we have to add T2 and T3, T2 and T3, T2 plus T3, and this T2 is made up of A dot B dot C. Over here there is an AND gate where T2 is A dot B dot C, and T3 is the combination of T1 and F2 dash. T3 is the combination of T1 and with F2 dash. And what is this F2? F2 is the not of this function. So if we see F2 dash, it is equals to AB AND gate and then OR with AC and then OR with BC. And for F2 bar, we have to perform the NOT gate over this. Okay, then T1 plus F2 dash, it comes into the category of F3. We get the F3 over here, and if we put the value of T3, and we put the value of T3 over here, we have the function for F1. So if we see what is the function of F1, the function of F1 is equal to ABC plus, or due to this OR gate, T3, where T3 is F2 dash or AND with T1. So T1 is again A plus B plus C multiplied by this function is AB plus AC plus BC bar. So this is the function of F2 for which we have to generate the truth table. So in the similar way for this this F1 and this is for F2, again we have to do, and F1 is nothing but this function, that is equal to A dot B plus AC plus BC. So this is F2. So for each input of A, B and C, for each combination of the input of A, B and C, we have to produce F1 and F2. So let's suppose we take the example of F2 because F1 is somewhat complex. So if we take all the values A, B and C 0, this is 0, this is 0 and this is 0. For F2 we have to put 0. A, B 0 and C 1, then A, B 0, this is 0. This is AC 0 and this is 0, again we have 0. So in this way for all the combination we produce F2, and for F1 we have to place the value over here. So if we take the example of all 0, this became 0, this became 0 and this became 1. So 1 multiplied by 0, this is again 0. So in this way for each combination we have to produce a truth table. So in the analysis we have to find out the function of the given circuit, and with the help of the function and for all the possible combination of the input we have to find out the truth table of the given circuit. So in this way we can analyze the combinational circuits. Next, these are some example of the combinational circuit which are frequently used in our digital system design. The first one is addition. In addition we use half adders and full adders and sometime BCD or decimal adders, subtractor, half subtractor, full subtractor, then multiplier, magnitude comparator, that is which number is greater in digital, like A is greater than B, A is equal to B or A is smaller than B, then there is magnitude comparator, multiplexer, demultiplexer, encoder, decoder, converter. These are some high-end circuit which is used in digital circuit design. Like if we take the example of multiplexer, multiplexer is nothing but the multiple line is selected with the help of selection line to the output. So this is the basic example of multiplexer. Similarly, demultiplexer that we see in the upcoming lectures. And converter is binary to gray code converters, gray to binary converter, binary to BCD converters, and these are the example of different combinational circuits. Now designing of combinational circuit. Previously we see how we analyze the combinational circuit. It is a circuit given, then we have to produce function and truth table. But in the design what we have to do, we have a problem statement or problem description. So according to the problem description we have to find the value, how many inputs are required, how many outputs are required for the given circuit. Then we have to find the truth table of all the combination of input, and we get the corresponding what is the value of the output that is desired for the circuit. Then truth table, then simplify the truth table with the help of K-map and different technique to produce the output, and then implement the circuit with the help of logic gates. With the help of different logic gates. So design procedure, first we have to define the problem, input, then truth table, then simplification of truth table or function with the help of K-map and other techniques, and finally draw the circuit. So next let us take the example of adder first. So this is a very basic circuit, that is half adder. So it produces the addition of two bits, two binary bits, and produce the sum as the output and carry. So if we take an example like we have to add 0 and 1, only 2 bits, 1 bit, 2 bit, A and B, X and Y over here, this is X and this is Y. So it produces two things, either sum or carry. So if we sum it then this is 1 as sum and there is no carry. The carry is 0. So in this case carry is 0 and sum is 0. So in this way for the 2 bit all the possible combination we take the sum and carry as the output, produce the function, and then implement with the help of gates. So if we take the example over here, this is input X and this is Y. This is a 2 bit input, so have 4 possible combination 0 0, 0 1, 1 0 or 1 1. For each case we have sum. For 0 0 sum is 0 and carry out is 0. For 0 1 we have sum is 1 but carry again 0. For 1 0 again sum is 1 and carry is 0. For 1 1, for 1 and 1, 1 plus 1 it is equal to 1 and carry 0. So sum is 0 over here and carry is 1 over here, as we can see over here. So we have two output function S and C out. So for S we have two minterms 1 and 2, and if we take the sum where the sum is equal to 1, the combination is x bar y and x y bar, x bar y and x y bar, and this is nothing but the XOR gate. So we have x XOR y over here, and for the C out we have only one bit over here. So for this the combination is XY. So the output is XY over here, minterm number 3. So in this way we have the function. We need an XOR gate and a AND gate to implement this circuit. So if as we know that XOR gate is a special gate, so sometimes we cannot prefer to use XOR gate. So we can use as well our basic logic gates like AND gate and OR gate. So for XOR gate, if we use XOR gate, we have the XOR of XY, and similarly AND of XY, it produces sum and carry, that is half bit. There's a half 2-bit addition is performed with the help of this logic circuit. And if we want to replace this XOR gate with the basic combination, so we have this x y bar by the end of these two circuits, and then sum, we have the sum and carry term over here. So in this way the addition of the 2-bit number is performed by the half adder. If we take the block diagram, it is seen over here, 2 input x and y and sum and carry as the output, and in this block we have this XOR gate and AND gate. So in this way we can design the half adder. This is called as half adder because it only adds 2 bit, but sometime we have, like in this case, we have carry as well. So if we have extra bit over here, then we have to sometime add 3 bit with carry one more. So we need, for the complete addition, we need 3-bit addition. So we, in the next slide, we are going to see how the full adder works. So this is full adder. So in the full adder, as we see in the previous slide, we need to add carry as well in the 2 existing bits. So we need a 3-bit addition in which either carry is either 0 or 1. So we have the 3 input now for the full adder. We have 3 input, x and y is the basic input, and C in is the carry that is produced by the previous addition of the bits, and sum and carry output, only 2 output over here. So we have the input x, y and C in. All the combination of 3-bit, we have 0 0 0, 0 0 1 to 1 1 1 1. Then produce sum and carry. As it is a adder, it sum all the 3 bits. So 0 0 0 is equal to 0, carry 0. 0 plus 1 is equal to 1, carry 0. Again plus we have 1, carry 0. In this case 0 plus 1 1, 1 plus 1 0, carry 1. Again same thing is over here, over here, and in the last we have 1 plus 1 plus 1, 1 plus 1 is equal to 0, carry 1, then plus 1 is equal to 1, carry 1. So we have sum and carry as well in the last bit. So in this way we produce the sum and carry as the output. So now we have, for the sum, we have the minterm 1, 2, 4 and 7, and for the carry we have 3, 5, 6 and 7. 3, 5, 6 and 7. So if we take it as 0, 1, 2, 3, 4, 5, 6 and 7. So we have the 3, 5, 6 and 7 over here. 3, 5, 6 and 7 for the carry out. Now again we have to produce the function. So for producing the function, if we take the K map, and with the help of K map, if we generate the function, it is seem like this, or we can directly take the combination. Then for the sum, it is x bar y bar C in, x bar y bar C in, x y bar C in bar over there, and in this way for the all possible values, all output as is equal to 1, we have the function like this, and if we sum up this function, this is nothing but x XOR y XOR c in. And for the carry out, we have this. Again, if we want to take the help of K-map, you can use K-map as well. So it is a 3 variable K-map. We have x, y and c in over here. 0 1 0 0 0 1 1 0 and 1 1. For c in, this is 0 1 2 3 4 5 6 and 7. We have 3 5 6 and 7, these ones are over here. For the minterm, we have to generate the output. So there is one pair over here and over here. So for this pair, we have for this pair we have x and c in, x and c in. For this pair we have y and c in, and for this pair x and y, we have x and y. So in this way, we can, with the help of 3 variable K-map, we can also sum up to generate this C out. So we have the function sum and carry, and now we have to implement with the help of gate. Here we require 2 logic XOR gates and the different AND gate and OR gate over here. So the circuit implementation is like this. For the sum, if we do not want to use XOR gate, if we want to use XOR gate, this is very simple. Use one XOR gate for x and y, and the output of x XOR y is given to the next XOR gate, which is the next input as a C in. So we get the x XOR y XOR C in. So this is the sum function. And if you don't want, you want to use basic gate, so there is requirement of very large amount of basic gate as well. We need a NOT gate over here as well, and the multiplication of these 3, then multiplication of these 3 and these 3, then sum up with the help of 4 input OR gate, and we get the sum over here. And for the carry, again we use basic gates x y and x c bar and x c in and y c in and then sum up, we have C out. So this is the implementation of basic full adder circuit, where carry is generated by this logic function, or then sum is generated by this and this logic function. So in this way we can implement the full adder. This is the implementation of the full adder with the help of 2 half adder. As we see in the half adder, there is again a NOT gate and a AND gate and a XOR gate is required, and in the full adder we need 2 XOR gate and different AND gate. So we can also implement full adder with the help of 2 half adder and an extra OR gate. As we can see over here, this is the half adder. This is one half adder where we required one XOR gate and one AND gate, and the output is x XOR y over here and xy over here. Now this input is given to the input of the this output is given to the input of the next full adder over here, and it can produce the x XOR y XOR this is coming z. Z is nothing but C in, carry in. So y XOR C in, or we can take at z as well as a C in input. Okay. So this is the sum. This is again the function of the full adder, the XOR of 3 functions, and for the output, this is coming over here, x XOR y, then it is multiplied by, this is multiplied by C in, and this is the output. And if we take as the OR of this function and this xy, we have xy XOR multiplied by XOR of x XOR y and dot C in. So if we solve this, then xy, this is x bar y plus x y bar multiplied by C in, and this is nothing but x bar became 0, x became x, then x y bar, and this is again became 0, y bar, and this again became 0, and we get the C in as the output. So in this way we can also make the full adder with the help of two half adder circuits. Now binary adder. Now we have the circuits of half adder and full adder, that is we are able to sum of 2 binary bits and 3 binary bits. Now in the in any binary addition there is multiple of bits, like in this binary word we have 4 bits, in this second binary word again we have 4 bits, and we have to add this. So we are able to add only 2 bits or 3 bits simultaneously with the help of half adder and full adder. So we need multiple half adder and full adder to perform this addition. So first we see how this addition goes on. Like this is the first bit, this is A1, AI is the first input, I is the representation of the place of the bit, like this is A0, this is A1, this is A2, this is A3, as similarly for B function B0, B1, B2 and B3, and now we have to perform addition. Initial carry is 0 always, because in the initial we have to add these two things, there is no carry. 1 plus 1 0, and we have carry 1, 1 plus 1 we have carry 1, and these 2 bits are 0, the 1 as it is and 1 as it is. So this is the sum that is generated, and this is the carry that is generated. Okay, so this carry, if we take this as I plus 1, that is I plus 1, that is it is shifted over this side 1, then we have 1 1 1, and next output carry is 0, because 1 is equal to 1, there is no carry, so it is 0. So next output carry is equal to 1 1 1 and 0. We require this Ci plus 1 when we make this binary adder with the help of half adders and full adders. So as we can see over here, this is the basic binary adder with the help of 4 half adders. As we can see, this is half adder 1, half adder 2, half adder 3, and full adder 3 and full adder 4. We have A0 and B0 as the input, and C in initial carry is 0, and it produces the sum term and produce a carry which is, as we can see, 1 plus 1 0 carry 1. This is C out, that is coming from at the output of this full adder, and this carry is going as an input, as the third input of the full adder, next full adder. So 2 input bits and the carry, it produce sum and again produce carry, or it can produce no carry depending upon the bits, and it goes into the next adder as 0 or 1. It is added, produce sum, carry, and this is the final carry. So that's we required. Final carry is 0 over the previous example. Over here, final carry is C out is 0, and the combination is for carry 0, 1 and 1. So this is carry, this is 0, 1 and 1, and initial carry is already 0, and it produces the sum as well. The sum is 1 1 1 and 0. So the sum is 1 1 1 and 0 as the previous example. So in this way we can use binary adder to perform the addition of 2-bit perform the addition of the binary number as many number of bit required. So if it is a 5-bit addition, we can use one more full adder over here. 6-bit addition, then we can add one more full adder over here in the combination of this. The next is decimal adder. So decimal adder is nothing but the again we use the same full adder ICs with the help over here, and with the help of generated carry, and in the BCD in the previous classes we see we have to add 0 0 1 when the sum is exceed 9, or there is a carry without when the sum is less than 9 but with carry. So give the input over here. In the full adder, in 4-bit full adder IC, this is nothing but the previous circuit, only this circuit is over in this IC. It produces sums and carry out. So sums is given to the next full adder, because we have to add 6. If there is a bit that is greater than 9, there is a result that is greater than 9, or it produce carry. So this combination of the logic circuit produce the corresponding corresponding output that gives the information that you have to add 6 or not. So how 6 is produced? As the output became 1, it is given to this bit and this bit, that is these two 1 and the rest 2 bits are 0. So this is binary 6. So whenever this carry is 1, it adds 6 automatically with the help of another 4-bit adder to the results, and the final BCD number is produced over here. And if there is any extra carry, it is given over here. Initial carry is 0 and initial carry is 0 again over here. So in this way we can perform BCD addition with the help of two 4-bit full adder ICs, and these 4-bit full adder ICs are made up of full adder circuits, as we can see over here. So thank you for this lecture. This is all for adders. This is all for today.